Okay, so what is the derivative if you want any physical quantity, let's say position, if you want to find the derivative, it would be dp by dt if you care about time. So rate of change of position is what people call velocity. So how fast is your car going will be something which you can measure by taking the derivative. So clearly derivative information is important, right? Derivative of velocity is acceleration. How fast you, how much are you pressing the gas pedal will be determined by dv dt, or the change of velocity. Okay, so here's how we'll do the derivative. We will use the Taylor series to do that. The Taylor series expansion. So now we're trying to estimate the derivative. Okay, so we've seen a Taylor series expansion about x. All I'm going to do is I'm going to replace x with xi plus delta x. Okay, this term was x earlier. I can put any value. I just chose to put a value which is delta x from xi. Okay, so we can expand this out as f of xi. Okay, the right hand side will remain the same. f1 xi plus delta x square f2 xi and so on. Okay, so this is, let me put another term because we'll need this when we talk about truncation error. So move it to the left so I can fit it in one line. Yes, that's my equation one. I'll be using it over and over again today. Now I'm going to also expand this function on the left side of xi. So xi minus delta x equals f of xi. Now I need to replace the delta x positive with delta x negative. So all I do is put delta x, the negative sign, f1 xi plus delta x squared 2 factorial f2 xi plus, sorry, it will be minus 3 factorial f3 xi plus so on. That would be my equation 2. Okay, so this is going to be our building blocks for the derivative. Now, one way of computing the derivative is to actually look at equation 1, which I wrote down there, and saying that I don't care about terms which are delta x square or smaller because the hope is that when you do a series expansion, a small perturbation, the higher derivative terms will give you very little contribution. And they'll do it because you see that you have 3 factorial coming, then you have 4 factorial, 5 factorial, and those terms become big, right? For example, when you looked at this example, you saw that there was a 5040, which is a very big number. So the hope is that anything on the numerator will have an insignificant effect because of that 5040. So the hope is that those derivatives will not really, or those higher order terms will give you very little contribution. So what we can do is we can just take one and ignore terms delta x squared onwards. So if you ignore that, we have f of xi plus delta x equals f of xi plus delta x f prime xi. Okay, so once we have that, now we can solve for f prime. Sorry, f prime of xi. So this is giving us a formula for the derivative of f at xi. Okay, and note that since we truncated it to delta x square, and this term is divided by delta x, the truncation error is of the order of delta x. The O means order, and so it's off by delta x. So if you choose delta x to be 0.1, it's saying that your calculations will be accurate to 0.1 or 1 decimal place. If you choose delta x to be 0.01, your calculations of the order of 0.01, which means that the accuracy would be 2 decimal places. That's what it means. It's all approximate. Okay, so this formula, which I wrote down here, has a name, and it's called the 2-point forward difference approximation. And clearly this is an approximation for PF PX. Okay, 2-point and forward difference. So we need to understand these terms. So what does 2-point means? It means that in order to find df dx or f prime, we need, yeah, question. I can't hear you. This is order. Oh, you got it? Truncation. Oh, truncation error, yeah. Oh, this one, okay. Truncation. So chopping off things, truncating causes this error. So okay, it's called 2-point because we're using 2 points, the value at 2 points to compute the derivative. So those points are f xi plus delta x and f of xi. Okay, and it's called forward difference because we need to look forward in x in order to compute that. So the forward comes because of the plus delta x. So you need plus delta x, look slightly forward, and look at the current point in order to compute the derivative. Okay, now you can do the same thing for the second equation I wrote down. You can say that I don't care about terms which are delta x square and smaller. And so I'll keep only the first 2 terms and try to derive another formula for f prime. So here is another formula. So from 2, ignore terms delta x square and lower. So we have f xi minus delta x, f of xi minus delta x equals f of xi minus delta x f prime xi. So I just ignored all the terms smaller than delta x square, and now I can solve and so this also is the truncation error of the order of delta x. And that's because I ignored terms delta x square and greater. But then when I do this, I have to also divide by delta x. So it becomes delta x squared divided by delta x is of the order of delta x. This is another formula for the derivative. It's called the 2-point backward difference. Yeah, one sec. Yeah, good. Okay, sorry. This is O order. Okay, so the notation is what's the order of the series? What's the highest? Well, this is basically tells you the you can say it's the error. This tells you how big is the error. Now we cannot give an absolute answer to this question. We can only say what is the order with respect to the value of delta x we chose. So if you chose delta x to be 0.1, it's going to be of the order of 0.1. If you chose delta x 0.001, it will be 0.01 and so on. Okay, so that's 2-point backward difference. You can see that it uses 2 points, and those are in the backward fashion because you use the value at the current xi, and also you look a little bit backwards, x minus delta xi. Okay, so one more before we start solving problems. There's something called the central difference approximation. So what we'll do is we'll go back to the 1 and 2. Okay, what we can do here is okay, so we saw that we ignored this quantity and this quantity. We just say we don't care about that. But what if we devised a method to eliminate that quantity, in the sense that our calculations will not even have delta x squared? It will all be cancelled off, taken care of, and the errors will only be of the order of delta x cube and more. And one way of doing that is if you subtract 1 from 2, let's say, or do 1 minus 2. Okay, I need a highlighter for this. Okay, so if you do 1 minus 2, so just subtract this. What you see is that this will carry over, this will cancel off, the f of xi will cancel off. This will become twice delta x, but here we see something happening, which is this term will be canceling with this term, right? And then this term will probably add with that term. This is fine, but we are getting rid of delta x squared. And so what I'll do is I'll do 1 minus 2 and write down the expression and see how it looks like. Okay, so f of xi plus delta x. Okay, that was the left-hand side. Then we saw that an f of x which cancels off. Then we have it was 2. So this is the first time I wrote was this. This thing will cancel off. So we'll have delta x minus minus. So because minus, so 2 delta x f prime x. Then we go back. Then we see that the third term cancels off. And then we have the fourth term. We'll keep that term, and then I'll truncate it later on. So we have delta x cubed, and the minus signs will become plus. So 2 delta x cubed divided by 3 factorial. F 3 xi. Okay, so I'm going to do this slightly different. I'll actually first write the formula for uh, f prime. It's going to be f of xi plus delta x minus f of xi minus delta x. I carried this thing on the other side, so we have, well, and I also have to divide by 2 delta x plus, sorry, minus. Okay, now I can say, I can basically uh, ignore this term. Okay, the reason I ignore is I say that, well, that term is going to be small enough that I don't care the effect of delta x square. So we can write this formula as f of prime xi is f of xi plus delta x minus f of xi minus delta x divided by 2 delta x plus, so this is how they'll write it, order delta x square. So the error is of order delta x square, which is nice because now if you can start with delta x to be 0.1 and your error is only going to be 0.001. So you get one more place accuracy just because of the way you expand it out and use the Taylor series approximation. So this is what we were after. This formula is known as two-point central difference approximation. So it's 2-point because you still need 2 points. It's got central difference because you need to look a little bit in front, x plus delta x, and a little bit behind x minus delta x in order to compute f prime x. Okay, enough of theory. Now let's see how we can use this information to do some computations. Okay, compute. So problem 3, compute the cosine x at x equals pi divided by 6. That's 30 degrees using a forward difference. I'm just going to put a short form forward difference for the difference approximation, a backward difference, and C central difference. Yeah. Okay. And so besides doing this, you also have to try different step sizes. Use a step size of 0.01 and 0.001. Okay. Now, sometimes you'll see in books or in the questions, this will be written as 1e negative 2, 1e negative 4. It means the same thing. 1e negative 2 is 0.01. So what we have here is essentially computing the value using those two. But before we do that, let's just compute the value of cosine x, the derivative, using the actual derivative, right? We know what the derivative of cosine x is. So actual value is dx of, or let me just put it this way. F of x is cosine of x. F prime x is negative sine x. And so f prime of pi divided by 6 is minus sine pi divided by 6 is minus 0.5. So we know that this is the actual value. And so we are going to compare the values we get with this value. Okay, so this is, by the way, a very contrived example because we know what the derivative is. In a physical process, you will not know the actual function and you'll have to approximate the derivative using these. So forward difference, we saw the formula is f of xi plus delta x minus f of xi divided by delta x. Backward difference formula is as follows. And then central difference formula. Using f of x equals cosine of x and two different step sizes, 0.01 and 0.0001, we get the following results. Forward, backward, central, delta x equals 1e negative 2, 0.5042 minus 4956 minus 0.499. 4956, 4999, and then step size of 1e negative 4 gives us 0.5004 minus 0.4995 minus 0.4999. So you can see that if you compare the actual value, which is minus 0.55, it closely matches with the value we obtained for step size of 1e negative 4. And these are close, but not quite there. Maybe the central difference is as good as these other ones, but these two are kind of inaccurate in the second decimal place. So this is how you compute, use the forward, backward, and central difference to compute the first derivative.